Okay, good evening, everyone. So thank you for joining us again tonight for our TensorFlow Project Showcase workshop. So for those who have attended last week, so we have covered basics of TensorFlow and how you can build your first neural network. So for today, we have a new topic to cover. So we're going to discuss image classification using TensorFlow. So if you are keen on analyzing images and be able to leverage capabilities of machine learning to analyze your image data. So this is the right discussion and workshop for you guys. So before we formally head straight to the main discussion, I'll just probably give a quick background on AI Pilipinas first. So as mentioned, AI Pilipinas, for those who are new here, we are a community of Filipinos who are helping one another to upscale our capabilities to learn the new approaches in machine learning and to also like help others to learn this new technology. And we aim to actually collaborate, build a collaborative AI community that will bring positive impacts to the Philippines and also to the globe, and to also make sure that we were able to grow as a global hub for AI research and development. So right now we have at around 1,800 plus members on Facebook group. So if you're not part yet of that Facebook group, please do join us via the link below. And you can also join us via meetup.com/AI Pilipinas. We have around 800 plus members there. And we announce all of our workshops and events through those platforms. So we have been creating and like organizing events for the past years since 2017, in which we were started the community. So we have been in different cities and we have collaborated with different organizations and partners such as Microsoft, Google, PLDT, Globe Labs, and among others. So last year, we also hosted our first machine learning hackfest. And since we are relatively stuck at home because of the pandemic, so we have created a new program for you guys to maximize your time and leverage new technologies such as TensorFlow. So we recently launched TensorFlow Project Showcase. So if you're not familiar with that yet, you can just go visit aipilipinas.org to know more about TensorFlow Project Showcase. So I'm just going to have a quick brief about that program. So if you are an individual or teams, you can actually participate this program. So if you have any projects or applications that you have built previously using TensorFlow, you can submit those as entries for this competition. You can submit multiple entries if you like, provided that all of them meet the eligibility criteria that we're going to share later. So participants must completely fill out and submit the project application review form, and the application deadline is on November 27, 2020. So as mentioned, all applications submitted should be your original work and haven't been submitted to any contest yet. So you can submit past projects or you can completely build a new one. And applications submitted to the contest should be publicly accessible via web or mobile, and it must be an open source project. So code should be uploaded to any publicly accessible repository such as GitHub. And the winner for this would actually be receiving some of the prizes, and it will be selected based on a panel judging and public votes. So what's the judging criteria for this showcase? So first is functionality. If your app work and if you were able to achieve the goal that you were able to define, and is a solution innovative, is the solution creative? So in terms of technology, how technically impressive was the application? Is it difficult to build? And did you actually use clever techniques or technologies to make sure that your application has a wow factor? And in terms of context of design, you were able to put thought into the context of like user experience and how will you design the interface itself. And for number four, 10% would actually be based on the public vote. So this is in total of like 100%. And winners would receive a support to take a TensorFlow developer certificate, which is worth 100 USD, and all accepted applications. So regardless if you won, and as long as you submit your applications, you will also get a chance to win prizes such as Google Home Mini and Chromecast raffle. So even just submit applications, regardless if you win or not, you still have a chance to win these exciting prizes. So what's our content schedules for the since October and this November? We will be having a series of workshop, and these workshops would definitely help you start your understanding towards TensorFlow and the entire ecosystem of TensorFlow. And on November 27th is the deadline of application submission. And December 4 is our panel judging and public voting, and we're going to announce the winner on December 11th. So as mentioned, we have scheduled a set of workshops for you guys. We started the workshop last week, and today we're going to discuss image classification and TensorFlow. Tomorrow, we're going to have your guest from India to discuss about sequences or recurrent neural network in TensorFlow. On November 7, that's next week, we have Wenhe from China who will be discussing building a TensorFlow JS application. So if you're keen on building apps on the web using TensorFlow, so you can this is a great workshop for you. If you're keen on creating mobile applications, you can attend Henry Ruiz discussion on TensorFlow Lite application. That's on November 14. Also on the same date, if you are keen on analyzing text data, text classification will be discussed by Tierno on November 14. So as mentioned, just go to the website, aipilipinas.org. So the links are there for the streaming links, and we appreciate if you can share the word to your peers so that we have more and more people who can understand this technology and to also have an interaction with all of these amazing experts from different countries who are joining who are joining this workshops and this TensorFlow Project Showcase program. So for today, we have again Rodolfo. For those who have attended last week, he was the one who discussed building their first neural network, starting with the basics. So for those who doesn't know Rodolfo yet, he is an experienced developer of tech solutions using automation, machine learning, web services, data extraction, and data analysis. He has served as a tech consultant for his local government and as a research assistant in applied artificial intelligence for the National Consortium of Science and Technology in Mexico. For several years, he has been actively participating in building AI and tech communities. For now, he's a lead ML engineer at Omdena, and he is also a Google developer expert for machine learning. So without further ado, let's welcome our speaker, Rodolfo Ferro.
Okay, thank you, Ralph. Thank you for the introduction. Welcome, everyone. Thanks for being part of this event, the TensorFlow Project Showcase, and welcome to this workshop, Image Classification in TensorFlow. It's a pleasure to be here. Again, my name is Rodolfo Ferro. Right now, I'm part of the Google Developer Expert community. So here you can find my contact if you want to get in touch. And what are we going to be building right now? So we're going to explore for this session how computers see what are images and convolutions and why these are important for computer processes if we want to identify and classify objects in images. And I will try to explain what happens at a high level for computers when we define mathematical operations over images to understand what's inside images. And then we will be jumping directly into the code and we will be exploring how convolutions work. And we are going to be building our convolutional model for a specific problem. So first of all, it will be very useful if we already opened the notebook for today's session. You can jump directly to bit.ly/TF Showcase CNNs, and this will directly redirect you to a GitHub guest in which you will find a Jupyter notebook that can be opened in Google Colab. So um, if you open this link, it will take you directly to GitHub Gist. This one actually. So yes, I will open the notebook already because it will be very helpful to keep it open. And but I will go back to the slides first. So I will just keep this open and I will go back to the slides. So again, this is the URL that we will be using. Actually, I will be sharing this URL with Ralph so you can share it. So, okay. Okay, I hope that everybody got this URL. So let's get started. First of all, let's try to understand what's an image. So we can think of an image as an array of pixels that it's compound, yes, by just values of intensity in colors or in grayscale that in a big view will create our perception of images. But yes, in a low level for the computer, it will be just an array of pixels. So for instance, if we have this image of a deer, if we try to zoom the image near to a near, we will realize that we are going to see actually squared values for each of the colors. And the idea is that for computers, this representation is very useful because we could get a high level representation that for us as humans could be an image, but in a very low level, this representation, it's just an array of number values that will be representing the image. For instance, in this case, we could think of a grayscale image that has values between 0 and 255, as we explored during last session with the problem that we were working on. And this also applies for color images. We can decompose images and think about the pixel values, and we will be finding out that instead of having just one single value between 0 and 255, the color pixel will be composed by 3 channel values, one for the red color, one for the green color, and one for the blue color. And the combination of intensities for each of the channels will create our perception of the color at that pixel value. Actually, as a fun fact, this has something this is something related with the biological part of our eyes, because as humans, we detect mostly those 3 colors, and that's why computers have combination of those 3 colors to recreate color images inside the screens. So now that we understand a bit about images and why this pixel representation is important, because at the end, if we are planning to work with images in our computers, we need a representation that our computer is able to understand. So this array representation, it's quite useful on that way. we can think of mathematical operations to keep working to process those images and to try in our case to try to help us to understand what's inside an image or try to identify a specific object inside our image. So with this in mind, we can think about some operations. Some of them might be just adding, summing up two images. We can compute a difference of an image. But an interesting operation, an interesting mathematical operation that we can apply to images, it's a convolution. Formally, a convolution is a mathematical operator that preserves some properties, but and it's also an operation that is defined over continuous spaces. So the formal definition is by creating an integral, but in finite cases, we can change that integral for a summation directly. So in our case, we are going to think about a two-dimensional signal that it's finite. In our case, we could think of an image. And let's say that we have an image represented by this green big square. So we can think of that we can think of this big green matrix as an image that only has pixel values for one channel. So we can think of this big matrix as a grayscale image. And of course, it will have values between 0 and 255. So the idea is that for a convolution, we define another matrix that will have different values. This small matrix, it's called filter or kernel of convolution, and the mathematical operation that is applied between the filter and the original image is that we are going to be swiping our filter along our image, and we are going to be just computing the direct matrix multiplication. So in this animation, we are seeing how the filter is being swiped over the image, the matrix multiplication is performed, and the output of this matrix multiplication will be creating a new output of the convolved filter over the image. So you might be thinking, okay, so this is just a mathematical operation that runs over images. Why this might be relevant? Because, and we will be looking this very soon, convolutions, depending on the filter used, will allow us to rescue some important features from the original image. And what will be happening with convolutional layers inside neural networks is that this convolution will represent a transformation and will become a feature map that will rescue these important features inside the images. When we start exploring the code, I think that we will be understanding better this part, because we are going to see how changing different filters will allow us to detect different things inside images. Maybe another specific operation that can be applied for images could be trying to subsample, maybe downsampling an image, like to preserve main information of an image, but keeping a smaller representation of the image itself. So we can do this subsampling with pooling layers. So the idea of pooling is just to define a submatrix that will be swiping again our big matrix that it's the whole representation of the image. And with this subfilter, usually we are going to be considering two by two submatrices, maybe 3 by 3 submatrices, depending on the size of the image. The idea is that this feature map may be a result of a convolutional filter or something. And when we want to apply a pooling layer, what we are going to be doing is just downsample the original feature map that might be the result of a convolution. So we can think of this swiping little matrix, and we can think of, for instance, the first submatrix. We can consider the values, and for instance, when we apply max pooling, we are going to take the maximum value, and this maximum value is going to be rescued, and we'll create a new matrix. In the case of average pooling, we're going to add up all the values and compute the average, and the average is going to be the value that it's going to be the resulting value, and it will happen for each of the submatrices that will be computed when we swipe this little submatrix. And the idea of these two operations is that first, with convolutions, I already mentioned that we are going to be rescuing some very important features from the original image. And for the subsampling pooling layers, what will happen is that we are going to be creating a smaller representation of the original image or result of the convolution that will preserve the important information of the image. And why it's important to consider pooling layers, because when we create a convolutional layer, we are not going to be working with only one filter. So when we create and this is an important thing to mention, and this is going to be more clear. This is going to be clear when we explore the code. But the idea is that when we create convolutional layers, we are not going to be working just with one filter, with one convolutional filter, but the idea is to create different filters. So if we create, for instance, 32 filters in our convolutional layer, this will create like 32 feature maps that will come out from those different filters. And the idea is that we start like growing our information, and by having some subsampling layers, like pooling layers, will help us to preserve the important information, but to reduce the representation of these important features that we are working on inside the neural network. So this is why it's important to think about these operations. So this is maybe a mathematical abstraction. Besides my explanation of how these operations work. But let's try to understand what happens or why these operations are useful. So for this, we are going to try to think at a high level what happens. And for this, again, let's try to think with this example, with this analogy of how our human brains work. So thinking of this image, if I show you this image, and if I ask you, okay, what's inside this image has been blurred. So if I ask you what's inside this image, maybe one or two or three people maybe can guess or say whatever thing that comes to their mind. But the idea is that a priori, we do not have like enough information to understand what's inside this image. But if I change this part by specifically showing you some parts or some features of the thing that is inside of our image, you start building an idea of what's inside the image. So if I change the image and I show you specifically this feature from the image, you maybe can start thinking about something because you are start to see more from the image. Maybe if I show you a different feature, for instance, this part, you start identifying objects inside the image. So you start identifying that there are hands inside our image. Maybe if I change the feature, with these different features, you start building a complete idea, a complete conception of what's inside my image. So in a very high level, as humans, we identify some features, some characteristics, yes, some features from our image, and we built the idea of association to identify what's inside of our image. So in this case, I only showed you three features of the something that was inside the image, and by showing you only these three features, you can assume, or you can come up to the result of saying, okay, inside this image there's a person. And in a very high level, what will happen with neural networks when we show neural networks a lot of images and we add these convolutional layers, what will happen is that in a very high level, these convolutional layers will help the neural network to identify features inside images like these ones. So these convolutional layers will, when I say that the convolutions and convolutional layers will help us to preserve the important features of an image or to identify the important features of an image, what will happen is that along the training of the neural network, these filters would be adjusted, and these filters will learn the features and how to map the important features between layers. And at a high level, this is what happens. So we can think of these convolutional neural networks to be working in a similar way as our human brains, in the sense that we identify some features of the object that we're looking at, and it will, by identifying and creating a compound object of these features, we can get to the conclusion of identifying what's inside an image. So this is what happens in a high level when we think about convolutions, convolutional layers inside neural networks for images. And an interesting thing that happens inside neural networks is when we have different convolutional layers, these convolutional layers learn different levels of abstraction. So let's think now uh, about a problem of identifying faces inside images. Well, if we have, for instance, three convolutional layers inside a neural network, we can think that the first layer, it's going to be identifying shadows in a very specific format. Yes, in a very specific format, and these shadows will help us in a second layer to identify more complete objects of more complete abstracted objects. For instance, in a second layer in our deep convolutional network, we're going to start identifying things like maybe noses, eyebrows, maybe the shadow of the eye, some parts of the mouth, etc. And as we continue getting deeper in the model with more convolutional layers, the deepest convolutional layers start learning representation of these features in a higher level. So for instance, in the third layer, we will be seeing that our convolutional neural network will be identifying like complete faces, right? So this is the idea of how convolutional networks will be working in a very high level. And I think that that's it so far. This is, I think, that everything that I want to explain so far. And I think that we will be jumping directly to the code for this session, so we can understand better how all these things are going to to be working. So first of all, we already opened our collab notebook, so um, I won't be explaining again like how Google Colab is working. If you attended last session, we already know a bit how Colab working. But well, anyway, first of all, I highly suggest you to create a copy. So you can go to File, save a copy in Google Drive, or maybe in your GitHub. And the idea of creating a copy is that since we are opening a copy directly from GitHub, it won't be saving all the changes that you apply to the notebook. But anyway, it's not a big deal. I think that you can always check again this recording. But yes, I highly recommend you to create a copy. I have already connected my notebook to the Google server. And an important thing to mention is that you can always verify that your runtime it's a GPU, specifically when you are creating deep neural network models or working with images, because these sometimes are kind of heavy processes for the computer. So using a GPU is always a good idea. So let's try to understand what happens. And for this, I will we will be quickly exploring what happens with convolutions. So for this part, we are going to load an image. So right now, actually, I'm just importing some useful Python packages, the NumPy package for numerical Python operations, the SciPy, because SciPy already has an image inside the NESC module, and Matplotlib to explore and visualize the image. So right now I'm just opening the ascent image that is already in SciPy, and I am just plotting the image. And this is the image that I am going to be working on. In my case, I am receiving this warning because I'm running the notebook directly from GitHub. So there's no big deal here. I will just say yes, run the notebook anyway. Your case, if you create a copy, you won't be watching that warning. But okay, so I have just loaded my image that I am going to be using for this exercise of exploring convolutions. And let me just, okay, there it is. So I am going to create a copy of the image. So I am going to save the new values for each pixel after convolving a filter over the image in this variable called image transform. So as I mentioned, I'm creating a copy of the original image, and I am getting the width and the height of the image. So that's it. I am extracting the shape of the image because I am going to swipe the filter over the image, and that's it so far. Right now, I have created some filters that you can use and to explore the values. And for instance, I have created a filter that it's, let me just change the format of this representation. I have created a matrix filter to have as a first approach and to explore. So you can see that this little filter, this kernel, it's just a 3x3 matrix that I am going to use to convolve over the original image. So for this example, I have created like by hand 3 different filters, and we are going to explore the outputs of applying these filters. But in the end, what will actually happen when we train a neural network is that we are not going actually to define by hand the filters, but what will happen is that along the process, the values of each filters are going to be adapting accordingly to what we already mentioned the last session. When we try in this machine learning paradigm to predict values and adjust the prediction and so on, that's the process that will be actually adjusting the values of the filters inside our convolutional filters. But for this practical example, I have three filters, and we are going to be exploring what happens with these filters. So I have already defined this filter, and I actually defined in this case a weight because I am going to divide the result of the convolution by 8. So I am after I apply the direct convolution to the filter, my last operation will be just to apply a weight over the convolution. And right here, I have my convolution. So let me explain to you what is going to happen in this part. I I am going to be swiping my filter over the image. That's why I have 4 cycles in here that go from the first pixel value to the size of the kernel of the image, sorry, of the complete image. And the idea is that I will start or I will initialize the convolutional value in 0, and I will start computing the product of each position of the filter with each position of the original image. So the idea is that I will take this first value and I will take this first value of the image and I will multiply these values and I will add the result to the convolution. Then I will take the next value, for instance, the number 2 with the right directly next pixel value and so on. So I can think of a complete multiplication of the filter over the image. And since I am swiping this filter over these 4 cycles, I can think of the filter to be swiped over the original image, and I'm computing the convolution values. The idea is that this convolution value is going to be assigned to the XY pixel value of the new image. And with this, we are going to get the output value of the convolution part. Just an important thing to mention is that as I am interested in preserving my range values of the pixels between 0 and 255, if there's a pixel value that is lower than 0, I'll just remap it to 0. And if there's a pixel value upper or greater than 255, I will just keep my pixel value representation of 255 just to remap the values and to keep my pixel values always between 0 and 255. And as I mentioned, just when I finish my matrix multiplication and so on, I just like apply the convolution. I just applied this way to the convolution, and that's it. So let's explore what's the output for this filter, for applying this filter to this original image. So let's see. I will run this part of the code. And this image transformed variable will contain the output of the convolved image. So let's see what happens. And as we can see, if we compare this image with the original image, for instance, we can see that the image looks brighter. And actually, it has been blurred just a little bit, but as we can see, the image as an output has remap the values of the image, so we can see a brighter image. And this is something that will happen. So it's okay. As we can see, a convolution performs a complete transformation itself and will compute an output of the original image. So that's an interesting thing that will happen, and that's why convolutions are important. So let's explore what happens when we change the filter. So I will change the filter and I will actually change the weight. So let's change the weight to 1. And let's think of this filter. So let me just rewrite this filter in something that looks more like a matrix. So let's think of this filter. So we have pixel values that are negative on the first row and 0 in the middle row and positive values on the last row. So let's explore what happens when we convolve this filter out. First of all, let me create a new copy of the original image so we can convolve over the original image. So let's see what happens when we apply this new filter in a convolution to the original image. And let's see what happens with the output. So we see that actually the output changes. And when we apply a different filter, we rescue different pixel values. So the idea of this specific filter is that we are going to identify that this is going to take like some of the borders of the whole image, so we can, so the image is not the result of convolving this filter to the image. It's not caring about pixel values, for instance, for the sky, or for the color of the wood of the stairs and things like that, but it cares about rescuing other important features, such as the borders of the image. Actually, we can see that are the right shadowed part of the borders, and this is how different filters applied rescue different properties. So again, if I create a new copy of the original image, and if I explore with one less filter, let's see what happens. So right now I'm changing the filter, and actually I think I can think of this filter as a transpose filter of the previous one. So if thinking of this transposition operation, we can think that the filter should rescue similar properties of the image. But let's see what happens when I convolve this new filter over the image. So let's keep in mind this filter, and let's see the new filter result. So yes, as we thought, this new filter that was actually a transposition of the previous filter preserves different information, but the same idea. This preserves actually the borders, but we can think of the bottom part of the shadow parts of the image. So the idea is that this filter is also preserving borders. So this filter applied inside a convolution to our original image won't care again about the pixel values of the sky, or the pixel values that represent this person that is going up the stairs, but it's going to identify borders on the image. So as we mentioned, in our theoretical part, maybe in a first layer, our neural networks are going to start identifying some shadows, and in another level of abstraction, they are going to be identifying more specific objects. And this is what happens with convolutions. So you can explore this part and try to define your specific filter for this situation, and see what happens when you change the values of your filter, and when you apply this filter in a convolution to an original image. So with this first part, we now understand a bit more how convolutions work for images, and how applying different filters will rescue different data or different features from the original image. So this is an important part, an important thing to mention, or to understand about convolutions. So now the pooling part will just take a smaller representation of the image, and we're going to explore that part when we start building our convolutional model. So first of all, we can jump now directly to build our convolutional model, since we understand how convolutions work. So first of all, again, I am going to import TensorFlow, just verify that we're using a latest version of TensorFlow. And for this part, for the previous session, we used a data set composed by images that are part of a fashion data set. So we worked with images containing like shoes, dresses, shirts, and things like that. So in our case, we're going to use actually another data set. So we are going to be using the MNIST dataset, which is a dataset composed by handwritten digits. So we have digits, numbers from 0 to 9 that are written by hand, and we have these digit values inside 28 by 28 images. So these are small images. So let's see. As we already know, the MNIST dataset will also have a log data function, as we As we saw in the previous session, this load data is going to split directly the data set into training images along with its labels and test images. So there's no big deal with this line if you were here during the previous session. But again, the idea of this is that we're going to use the training images to show these images to our network, and our neural network it's going to learn from these images the how a number looks like. And at the end, after the training, after showing our network a lot of images, we are going to be using these test images to actually to test our model and to see how it performs with images that it has never seen. So this is the idea between these training and testing images. So we have already loaded our data set. So let's see how these images look like. So for instance, I will load our first image from the training data set. And the matrix representation, I will see that I will have values between 0 and 255. And the image representation of the image, we can identify that this is a number 5. So let's try to explore another image. An important thing to mention is that the training images subset is composed by 60,000 images, and the test images subset is composed by 10,000 images. So we can see how an image looks with a range between 0 and 59,999. So let's explore, for instance, the 3000 index, and let's see what image is this one. So we can see that this is a number 9. So if you want to explore a bit more the data set, you can just change the index and explore the pixel values of the image and how the image looks like. So we can see the label of the image. So yes, this corresponds to number 9. So before creating or talking about our model, there's an important step in which we have to pre-process or to prepare our data to feed our network. And what we are going to do is just to normalize the input, because for a neural network, it's easier when it works with values between 0 and 1. So we are just going to remap the values from 0 to 255. And if you attended our last session, you already know this part, but this will help our neural network to work better with the values. And also, I am going to add just a set of brackets inside the the whole list of images. So this is why I reshape the values. So actually, I'm just adding one dimension to this part of the images. So actually, we are having, and I think that we discussed this a bit, this part during last session also. But the idea is that I have images that have one single channel, a grayscale channel. So we have images that are little matrices, because we already know that that an image is an array of pixels. So we can represent an image with this as a matrix of 28 by 28. So what I am doing here is just adding or specifying that this image contains just one channel, a grayscale channel, for each of the 60,000 images for the training images and for the testing images. So this is what I'm doing here. Just what happens internally is that I am adding a pair of brackets to extend the dimension of my representation of the set of images, but that's it. And then I am normalizing the images by dividing the complete pixel values by 255. So this is that's what is happening in this part. So if I run this code, actually I can again verify my pixel values. So if I actually I will copy this part. So just to verify that these operations are preserving my representation of the image. Okay. Let's see if this works. I think that I am getting an error because of the my extension of the dimension. So let's try this. Let me just add one more index. So this should work. Well, actually, I'm changing my representation because of the extension of my dimension, but at least I can see that I'm preserving the pixel values, and these are remapped to values between 0 and 255. So I've just changed my representation of the image by extending this dimension, which actually changes my whole format, but that yes, that's what happens. Anyway, thinking about our convolutional model, for our last session, we had an introduction on how neural networks work, of how uh, some computing units, what we called neurons, could be specified with the dense layers that are inside the Keras module inside TensorFlow. So the idea is that we built a sequential model in which we took the complete matrix representation, and we like flattened the representation into a vector containing all the pixel values, and this vector directly went as an input to our neural network. So this input value fed our neural network. So what will happen for convolutional neural networks, or when you work with images usually, is that you do not need to flatten or to change the representation, because the idea is that, as we previously mentioned, there could be objects that are or features inside our image that depend on the neighbor value of the pixel. So if I have some brighter pixel value at this point, and I move to the upper pixel value, maybe this upper pixel value will have a similar value. So the idea is that neighbors to a pixel will preserve, at least we think, or will change the values in a softer way. It's not going to be like a very straightforward jump on the value of the pixel. And the idea is that if we're going to be using convolutions, these convolutions are going to help us to identify these features by working with these pixel values, as we previously saw with the. I think that I will delete this cell because it's taking a lot of space. But okay. So as we saw with how the output values of applying a convolution to an image are working, we are not going to be working with an input layer that actually like flattens the representation value of the image. So we're going to work instead with convolutional layers. So for this part, let me talk a bit a model that actually we're going to be using as our first approach or inspiration for this part. So this is one of the most famous models because it's one of the first convolutional models that were presented to the world back in 1995 or something like that. So this is a convolutional model created by Jan LeCun. Jan LeCun, it's right now he's a researcher. Actually, he's the head of the AI research part in Facebook. So he created this model called LeNet 5 because it's a neural network that has convolutions inside. So let's explore or understand a bit this structure and how this structure represents a convolutional neural network. So the idea is that he worked with images, with handwritten digits, and he had an input image. And what happened is that he created a number of filters or convolutions that were changing the values of these filters when along the training, when we start the training of the image. I have already mentioned this. When we start the training of our image, the values of these filters are changing and adapt to detect features from the image. So in a high level, these filters learn the important features of the image, these filters. So what he did is that he created a convolutional layer in which he created 6 filters. So each of these filters adapted its values, and each filter was applied to the input layer. This created these 6 output layers, sorry, these 6 output images, one after applying one of each filters to the input image. So far as the output of this first convolutional layer, we had 6 output images that come from the input image. And this is something that I mentioned, and this is why pooling layers are important. We can think that if we apply, first of all, we have only one image that fits our layer, and it's processed with 6 different filters that are convolved to this image. And as output for each filter, we're going to have a new image, right? So after convolving the image, we're having 6 different images. So instead of getting a smaller representation of the image features from this single image, we're getting 6 outputs. So the idea of pooling layers is that in some way we subsample the original image, so we're not keeping like growing the number of values for our image, because after pooling we apply now 16 filters. So instead of having 6 filters, we are going to end with 16 different images. So this is why pooling will help us to downsample the representation that comes out from filtering after convolving the image, from the output after filtering. It's important to downsample the representation, but preserving the important features of the image. So that's why pooling is important. So in this part, it's called LaNet 5 because we have one convolutional layer and a pooling layer, another convolutional layer with a pooling layer, and at the end, 3 dense layers. And these 3 dense layers are composed by directly 120 neurons that, as we previously saw from the last session. So the idea is that performing this step from this second max pooling, jumping directly into this first dense layer. In this part, we are going to need to apply a flattened layer, so we can like flatten actually our representation of these output matrices into a single long vector. So we will have our 3 last dense layer with 120 neurons, with 84 neurons in the next one, and finally for our output layer with 10 neurons, that it's our output layer for our 10 classes, and that's it. So the idea is that we are going to take our previous model from our previous session as a base model, but we're going to understand how can we implement convolutional layers inside TensorFlow. So for this, inside Keras, inside the layers module, we will be able to find convolutional layers actually in 1 and 2 dimensions. In 1 dimension, if you're working, for instance, with different kind of input signals, such as audio, it's very helpful to use convolutions, for instance, for audio data and things like that. So in the layers module, you will be able to find 1D and 2 dimension convolutions, and 1D and 2D pooling layers. So this is how we are going to be working with our convolutions. I will delete the second layer that I have here. So first of all, I am going to create a first convolutional layer inside my sequential model. And the idea is that I will receive an input image of 28 by 28 with only one color channel, my grayscale channel. My activation function is going to be Rolo. We already talked a bit about this during our last session. And I am going to create how many? We're going to take this LaNet 5 as an inspiration. So let's say let's take the 6 filters that Jan LeCun is using for this part. So we are going to create 6 filters that are 3 by 3. And after this layer, we're going to use the relo as the activation function. And again, we are going to receive for the input layer an input image with these dimensions. So after this convolutional layer, this is how we create a convolutional layer. After this convolutional layer, I am going to create a max pooling layer. So actually, we will find average pooling layers, mean pooling layers, and so on. So for this, we're going to apply a max pooling layer 2 by 2. So it's going to take a submatrix of 2 by 2, and it's going to take the maximum, and it's going to perform the subsampling of the image. So this is our first layer, our convolutional layer with subsampling. If I want to add a second convolutional layer, because in this part, Jan LeCun perform a second convolutional layer, I can directly, actually, I think that I can copy directly this layer, and I would just delete the input shape, because this input shape is just specified on the input layer. So our input layer is directly a convolutional layer. That's why I need to specify the size of the input data. But for my second convolutional layer, the input is going to be the output of the previous layer. So that's why I do not need to specify the input shape. That's why I deleted this part. But the second convolutional layer actually has or performs convolutions with 16 filters. So I am going to change this part, and I will add 16 filters that are 3 by 3 filters, and with the relo activation function. Then I need to apply a max pooling. So again, I think that I can directly copy this max pooling layer. And so far, we are at this point. We have applied a second convolutional layer, and we have applied max pooling. So we're in this part. So then we need to apply flatten layer, so we can like flatten, like squeeze our output of this last pooling layer into a vector that is going to be connected to our next dense layer. So here I perform a flatten layer, and after this we are going to apply a new dense layer. So let's create this layer, layers dot dense, and we're going to create a 120. Let's add 120 neurons, and activation. Let's specify that we're going to use the relu activation function. Then our fifth layer, actually not our output so far, we're going to, oh, actually what happens is that when we flatten when we flatten the layer, this is going to translate into the 100 neurons. We're going to change this. So actually, instead of actually having 100 in this part, we're going to have 84 neurons in this part. So let me just change that part. Output, and you will see what I mean by saying that the flattened part will have the 128 neurons. So let's work with this model first, and actually we can explore by adding or modifying the layers and filters and so on. So let's start with this first model. So let me invalid syntax. What's my invalid? First, yes, absolutely, comma. Let me see if I am missing something else. No, I think that's it. Okay, so I am creating my convolutional model. So actually, if I add cell code and I explore my model by calling this its summary method, I will see what is happening with the output of each of the layers. So I can see that after applying the first convolutional layer, I will have a tensor of 6 output images of 26 by 26. After downsampling by applying the pooling, I am getting smaller images, but I'm preserving the size of my tensor. Then if I apply more filters to those images, my output changes and so on. So this flatten, actually, instead of having 100, we are getting, after flattening the vector, an output of 400 neurons, and then we have our 84 neurons. Thinking of this model as an inspiration. Actually, if we want, we can change the model and just add our 120 neurons if you feel more comfortable with this part. Actually, this model building, it's a whole part. But the idea is that after building our convolutional model, we will see that this model will have around 60,000 parameters that are trainable, which means that when we start training our model with our training images, with our example images, along the training, this will be modifying or varying the values of these parameters. And most of these parameters will be inside the filters of the convolutional filters that we are working on. So we can compile again our model with the same parameters that we already talked about during our previous session, and we can start fitting the model. So for this, I will fit the model for 5 epochs, and let's see how our model performs after these 5 epochs. So let's wait 1 minute. So we can see that since we are using a GPU inside Google Colab, it takes around 4 seconds to train each epoch. So let's see. For our training images, we can get a very low error and a very high accuracy. So, but we need to verify or evaluate our model with the test images that are images that our model hasn't seen before. So we can again evaluate our model and see that our model performs with a 98% of accuracy. So actually, our model is supposed to classify in a very nice way. So let's try out the model again. I am using code that we already explored from our previous session. So let's see. I can specify an index to predict. So in the testing images, my image for index 30, it's going to have a label number 3. This is how my image of at index 30 looks like. And my prediction, again, I am going to call the predict method inside the model. And I am going to apply or try to predict. Let me just rewrite this in image. I am going to take the test image at that point, and I am going to extend my dimension so I am able to fit my neural network, because if you remember that I reshaped by adding just one set of brackets in my representation of my tensor of images, that's what I'm doing here, and I can use directly this input image to be predicted. If we remember this prediction vector, let me cut this part. Instead of cutting this part, I will just print my prediction. So if we remember, this prediction vector contains like there's the result of mapping probabilities to each of the categories. So at the end, what we want is to compute the maximum argument of this vector. So see the maximum probability and verify the associated index to that probability. So for instance, for index 0, 1, 2, 3, where this is our maximum value of the prediction vector, as we can see. And this is going this is what we're going to take as our prediction output. That's why I take the maximum argument of the prediction vector in the this is why I am getting a prediction and as a prediction and number 3. So let's explore what happens when I change the index value. For instance, I get the label is number 6. Clearly this is a number 6, and my prediction it's actually a number 6. So the maximum probability associated to a class is the class to number 6, and this is how our convolutional model is going to perform. So okay, let's summary what's happening so far. We have explored already how convolutions work with the first part of the code by applying some filters to a sample image. In this part, we have already loaded a data set that we are using to train our convolutional neural network. And we already know how to build our convolutional neural network by adding convolutional layers. An interesting thing to explore is what happens when we add more filters. For instance, 64 filters instead of only working with 6 filters or 16 filters. What happens when we add more filters? And does this performs better with our model? That's an interesting question that you can try out. So let's see. But the idea is that now that we know how to create convolutional models, you can keep exploring how these convolutions perform in these models. And actually, as we can see, by adding more filters, we have more outputs. So we rescue more features from the original image. So we can see that in a first quick view, this performs better than our previous model. So actually, our model is supposed to perform with a 99% of accuracy. So yes, so far you can explore on how to create your own convolutional model and try to build your convolutional model for a specific example or to solve a specific problem and so on. So an interesting thing that we can explore as next steps in this part is to try to understand what is happening in the middle layers. What happens in the convolutional layers? So for this, I have added an extra part of code in which I will take some images and I will feed them through a neural network, but my neural network convolutional layers are looking at from our input image. So this will clarify to us what convolutional layer it's going to be paying attention at to when we work with an input image of the layer. So let's see. What I am going to be doing in this part is just like specify the index of 3 images that I am going to be using to feed our network and to verify the convolutions. So in this part, I will specify the number of convolution that or the filter that I am going to be looking at. And for each output layer inside of the layers, I will create a new activation model that as an input, it will take the same input as that my original model is going to take as an input. But my output of the model will be each of these output layers. So the idea is that I am going to feed my original model, my trained model, but I am going to stop at some point with the when a convolution is performed, and I am going to look at that convolution output. So that's what happens in this block of code. So as you can see, I just apply the convolution for my images, and if I run this code, I should be supposed to see what my filters are looking at for these images. For instance, if I feed my network uh, with a number 6, what my convolutional filter is going to be looking at, it's maybe on this part, like the curve that is performed for the number 6, maybe the shadow generated on the left part of this number 1, and maybe the down parts of the number 8. And as we can see, and as I mentioned in this part, in abstraction, our network, it's going to be learning at a high level some representations or some important features that represent in this case, our digit number. So that's it. You can explore by modifying the convolution number, and we should get different results. So our different convolutions are going to be looking at or rescuing different features from our input images. So in this case, we can see that the convolutions are going to be looking in the first part at the top part of the number 1. So in this way, we can think that our convolution is going to know or learn the part where a number 1 usually starts. We can think of that part in this way, and so on. Each convolution will work differently with each input, and yes, that's what will happen. So we can keep exploring according to the number of convolutions that we have, and start understanding what our neural network is going to be identifying, or what features is going to be rescuing or learning from our input images. So you can keep exploring with different images also. So let's think of our first image. Actually, let's explore the very first 3 images of our test set. So our first image is a 7. Our second image is I don't know what number is this. Our third image is a number 1, or at least it looks like a number 1. I'm not sure. This looks like a number 2, I think. Maybe if we plot this in here, just to verify that this is a number 2. Yes, actually it's a number 2. So yes, actually we're looking that our convolution, it's specifically paying attention on this part of the number 2, and so on. So this is an interesting way to explore what happens inside the convolutional layers for our network. And that's it. I think that with this, you should be able to understand what happens with convolutions and how convolutions work, and more specifically, how convolutions inside a neural network that has convolutional layers work. Because in this part, we can see what convolutional layers are looking at when we feed our neural network with an input image. So far we understand that all the convolutional part. We already know why convolutions and pooling are important, because in a high level, this convolution, actually we can go back to this example, because in a high level, the convolutional layers will try to rescue some important features in order to, in a high level, identify what's happening inside our input image. So we now understand that part. And finally, we now know how to build a convolutional layer using TensorFlow. So I think that so far we have completed what we should be looking at for this session, and in a nice level of understanding of what's happening. So I think that actually I'm going to go so far with you, Ralph, to see if there are any questions inside the chat, or if we need to explore a specific thing or something.
Okay, yeah. So we encourage anyone who's actually joining us tonight to ask questions. So you can message either if you're on Facebook Live, just message on the comment so that we can see. If you have any questions, if you're on YouTube, just like message on the comment box if you have any questions. I think while waiting for some questions, I have a questions. I have some question, Rodolfo. How do you deal with since you already shared a while ago using MNIST dataset, right, which is definitely right now it's a grayscale. Is it the same? Would it be the same approach if you're using a colored image? How do you deal with that?
Oh, that's an interesting question. I think that I will go back to my coding part, my coding part. So let me show you again my notebook, and let's see in this part. I'm not sure. Can we share again? Oh, there it is. Okay, thank you. Okay, so in our case, if we are planning to work with color images, some things are about to change. If I load a data set composed by images, of course, I can explore the data set and things like that. In this part, the important thing is that when we reshape the images, of course, the reshape should have or should needs to have specified the number of channels. So if we are planning to work with RGB images, we first of all are going to have a reshaped tensor of images that will have these dimensions, the number of images in our subsets, the size of the images, and the number of channels. And when we create our model, we just need to specify the input shape in this part. So if we are going to be working with 3-channel images, RGB images, we just need to change this part, and everything else should be working without any problem. So yes, I think that this is the main change that you have. And yes, that's it actually. The good thing or the interesting about TensorFlow and its high-level API Keras is that we do not need to make a lot of movements and a lot of programming stuff, because it's created to solve problems through AI in a very simple way. At least with the coding part, it's thought in this way.
Okay. We have one question from our audience, coming from Jonardo Astor. How epoch affects the learning process? Do they need to fix it, especially if they're dealing with images?
Sure. Okay. First of all, we already talked a bit about this part during our last session. So we mentioned that when we train or when we fit our model, this is an optimization process in which we try to predict from our images. We compute an error, and we use this error to fix the connections inside our network. Let's say in our case, the connections between the dense layers and the connections or the values of our filters and so on. So the idea is that we want to minimize this error. So if I say I'm in Mexico, I'm in Mexico, I'm in Philippines, and our world is a function that represents the relations between our data. If the minimum is in your place, in your house, Ralph, and I am right now standing in my house, if I just train my model 5 epochs, it's like trying to take 5 steps approaching to your home, where is the minimum that minimizes this error. So the idea is that adding more epochs should actually perform better on your model, because you are approaching better to the minimum of this error. So if I take more steps to your house, I will get closer to your house, for instance, right? So thinking about minimizing this error. So actually, these epochs affect this learning process in the way that if you have more epochs, you start having less errors, or your loss minimizes and your accuracy should be maximizing. This is the general idea, but at some point, as we discussed on our last session, At some point, your model could overfit or could stop training because it could have raised a maximum of accuracy that it could reach, and so on. But this is the idea of how epochs affect the training process.
Okay, thank you so much for answering that and for reiterating about the epochs. I have another question. We have another question from Ivan. In regards to image data, is it required to have all of the images to have the same resolution or same image sizes?
Yes, actually, what happens is that our input layer has always a fixed input shape. So the idea is that yes, preferably we always have to prepare the data or to pre-process the data in order to have all images from the same input. There are some specific architectures that have some process inside that allow you to work with data that has different input shapes. But the idea is that in our convolutional models, we usually work with always a fixed input shape. I think that you're muted, Ralph.
Okay, thanks. Another question from Fidel is how many training images are needed minimum for a successful model to work? For example, if they're doing some like classification of like lettuce and lettuce with has like a disease, what's a common like practice in terms of creating your base data set if we're dealing with image classification?
Okay, that's an interesting question. Okay, first of all, yes, what happens with neural networks is that, as we mentioned on our previous session also, we can think of these models that they learn by looking at examples. So you can think as a kid looking to a dog, and the mother's kid says like, "Hey, son, look, that's a dog." So what happens is that if the kid only sees one time on his life, only one time a dog, it will be very difficult for the kid to identify a dog if the next time he sees a dog. But if his mother tells him like, "Hey son, that's a dog," every week that they see a different dog, the more examples of a dog the kid sees, the better he will identify how a dog looks like. So the idea is that the more number of samples that you have, the better. At least it depends on how robust is the problem that you are trying to solve. But if you are planning to program directly using TensorFlow your own convolutional model, I think that's maybe I could recommend you to try gathering at least 200 images for each sample if you want to have something like reasonable. And it depends because actually, when we work with, for instance, cloud services, Google also has computer vision services in the cloud. They usually do not use many images. I think that if you upload like 30 images of one class, for instance, healthy lettuce and 30 images with lettuce with diseases, what happens in the clouds is that they actually translate a trained model to the domain of your specific problem. So this is why these cloud models usually take less input, they take less sized data sets as input data for the neural network. If you want to try this, you can, instead of building a complete model from zero, you can think of using a pre-trained model because TensorFlow already has pre-trained models, and try to adapt this pre-trained model to your specific domain. And in this way, you can think of using less number of images on your training data sets.
Okay, thank you so much for answering that, Rodolfo. Another question is, in terms of like measuring performance metrics for images, do you guys also like still use confusion matrix, or like it's just purely accuracy that you're measuring? Are there any other performance metric when you deal with image data?
Yes, actually, that's a very good question. Yes, let me think. I think that if I want to right now write the code, for instance, to see the performance using a confusion matrix for this specific case, it may take a while because I need to export some other packages. But what I can do is just let me change my window to my other monitor, and I can open a notebook that I already have that performs a confusion matrix, so I can explain what happens in this part and how you can build this part to the matrix of the model. So just give me one second while I just open this notebook. And my research folder. Okay, here it is. I think that I found my folder. It's loading. It's loading. Just give me 1 second. That's a very good question. Actually, thinking about model performance in matrix, it's a very important thing because we need to care about how our model is actually performing. So let's see. I think that this is the good one. I'm opening it in Google Colab, and I hope that it still has the confusion matrix because I haven't opened this notebook in a while. Okay, let's see. It's loading. Let me try to move this here. Okay, it's loading GPU info. Okay. Okay, so first of all, I was performing some research on human-centered computing. So I have been exploring some very deep convolutional models to understand facial expression and emotion association between persons. This is a project that I've been working on for some time. Actually, from this research, I developed a project that is, I think that it's being used inside the psychology department of one university in Italy, I think. But okay, the idea is that I am working with a data set of people. Here I can see that when let me see, when I fit, this is also an interesting thing. When you fit the model, you can also save the training history, and you can plot the history to see the performance along epochs or how the training is performing. So this is an interesting that you can also explore. You can do a bit of research in Google, just like search how can I plot the history when I feed my model, and you can get plots like this where you can track the whole process of minimizing an error and growing the accuracy. For instance, I trained my model for 150 epochs. So as you can see, the epochs are relevant, and the model continues performing better. But the idea is that when I test the model, besides performing some predictions, I would like to get a whole view of how my model is performing. So a confusion matrix will help me with this part. A confusion matrix looks like this. The idea is that I will have a true label, and I will see the number of images that are associated with this class. For instance, in my case, the younger images from the total of images, how my model performs. And for instance, my model from the whole anger images, the 85% of the times, my model identified anger images as anger images. In the rest of the time, my model confused some images with neutral images or sadness images. And this can be applied for each of the labels. So this is a confusion matrix. For instance, the 100% of the times, my model always identified a person expressing happiness. So in this case, we can see that this confusion matrix at least help us helps us to identify whole performance of our model. So yes, this is another important matrix that you can explore. And if you want to explore this part, let me just share with you what you can do. You can import directly the scikit-learn package. It's already installed in Google Colab. And you can import from the metrics module the confusion matrix. And the idea is that you just create a confusion matrix and you pass as arguments to this function the labels that are the predicted labels and the real or the original labels. And this will give you back a matrix containing the values. Now, if you want to plot the confusion matrix, you will need to do more magic using matplotlib and things like that. But yes, you can plot a confusion matrix like this one using this specific example. But yes, again, the matrix of your model are important. And I hope this helps with the confusion matrix, like explaining what is a confusion matrix and how it works, and by giving you at least some reference of how you can build your confusion matrix. If you Google confusion matrix scikit-learn, you will find the code that you can add to this Google Colab. Yes, I hope this helps.
Okay. You shared about a while ago regarding pre-trained models. If you're going to jumpstart creating TensorFlow projects, will it be a great start to just use pre-trained models, or is it always a good start to start from scratch? So, what's the usual process of like workflow when you're creating those type of models for images?
Okay, I think that it may depend on your problem, because in my case that I am working actually with some model architectures, I always like to work from scratch and to understand what's happening between each of the stages of my models. That's why I like to start with from scratch. But if you are planning to solve a specific problem, you can also think always of exploring with pre-trained models. You will find actually that TensorFlow always has a lot of pre-trained models. One of them, and I am almost sure, like at least 70% sure that you will be using for next sessions, at least when you build your JS app or your TF Lite app, you are going to be exploring a pre-trained model called MobileNet. It has a specific structure, which it decomposes the convolutions in a more computer efficient operations, let's say. But the idea is that this model is already implemented in TensorFlow, and this pre-trained model that is already added inside the package could be important. The complete model that has already its weights trained could be important, which could be imported. And the idea is that you can retrain the model with the previously trained weights of the model to adapt this pre-trained model to your specific problem. So it's like to adapt this model to your specific domain. And yes, I think that this is a good idea. If you are planning to solve in a very efficient way, or maybe if your data set is not that big, you can always think of a pre-trained model that knows that you know that performs well for classification problems, and just feed the model with your data set and retrain the model with your data set. So yes, it's a good idea.
Okay, I think last question. So for those who are here that would want to explore more image recognition, what are your suggestions, tutorials that they need to look into, and what architectures that they need to like explore to progress?
That's an interesting question, because there's a lot of people that keep working and exploring and creating new neural network architectures that perform better on some specific cases for image recognition. I think that if you want to, oh, first of all, always I highly recommend you to explore the TensorFlow blog and the Google blog, because they always share like some advances on images. Actually, one of the most popular models that uh, came to light back in 2015, I think. The Google Net model, it's one of the Google's implementation, and it performs awesome for images. You can explore several websites that will help you for this part, and to see what's the state of the art of what people are implementing about these models. One of them that I usually like to look at, and actually I'm subscribed to their newsletter, because that's how I get updated on what happens in this part. There's a website called paperswithcode.com, and you will be able to find some research that is published by people. And the interesting thing is that you will not only find the research part. That's why it's called papers with code, because you are going to find the repository with implementation, so you can explore some implementations and state of the art of application of machine learning, actually not only for images, but for other domains.
Okay. Thank you so much, Rodolfo, for your time spending with us tonight and morning there in Mexico.
Yes.
And yeah, I think we're good. Thank you so much. And I hope everyone learned here today and start working on their project and start also exploring image recognition using TensorFlow. Thank you guys, everyone who attended this talk, and see you on our next workshop. Bye bye, guys. And thank you so much, Rodolfo. Bye bye.
Thank you. Bye bye.